Okay, so now that we know about Lewis dot structures, how to draw molecules, and do they have dipole moments, asymmetry, symmetry, we can start to look at the properties of these different molecules. And the properties are going to deal with how well or how not well they attract each other. And those are going to be intermolecular forces. So intermolecular forces are going to be forces that attract one molecule, one ion, one particle to another particle or ion or molecule. Let's make that a little bit bigger. Okay, so there's a lot of essential knowledges here, but that's pretty much the main idea. Okay, to give you a context about intermolecular forces, if you wanted to vaporize would be making H2O liquid go to H2O gas. Well, it's still H2O. You're not breaking any bonds inside the molecule. All you're doing is breaking bonds that attract one water molecule from another water molecule. And it takes energy to do that. It takes 41 kilojoules to get 1 mole of water to go from a liquid to a gas. But it takes 930 kilojoules, tremendously more energy, to be able to break the bonds inside of a water molecule. So that should give you an indication about strength. So the strength between molecules, what attracts one molecule to another, is not nearly the same as the energy associated with attracting one atom to another atom inside of a molecule. And of course, these numbers would change depending on what type of molecule it was and what type of atoms and all that. Okay, so typically we can kind of think of these different intermolecular forces. And by the way, no one uses the word intermolecular forces and writes that down. So from this point on, we're going to be using the term or the abbreviation IMF, okay? So intermolecular forces. So if you would have an ionic compound, Na plus to Cl minus, that repeating lattice structure, that's a very, very, very strong, not only actually is it an intermolecular force, I guess you could kind of consider that in some respects a intramolecular. It's not a molecule, it's a lattice structure, but it's a very strong attraction, okay? Does it have to be NaCl? No. So it could be still ionic, but maybe with polyatomic ions. So still positive charges attracted to negative charges. The next, typically the next strongest intermolecular force is ionic dipole. And the most common one that we'll deal with is water, which has a dipole moment. So dipole, so that's the dipole part. And then the ionic part would be maybe some kind of salt that's dissolved in water, and the Na plus would be very much attracted. And we like to use a dotted line to show, I don't have really much of a dotted line there, but a dotted line to show the attraction that's more intermolecular. Could we throw the chlorine in there too? Yep, we could. So let's go maybe use the chloride ion here. And it has that again. We'll use that dotted line to show that attraction. So do you see that some of those pluses and minuses are in parentheses and some aren't? The ones that are the Na plus and Cl minus, those are truly positive and negative charges. The charges associated with water are partial positives and partial negatives. Okay. So then our next category of intermolecular forces is dipole-dipole. Well, anytime you have one molecule that has a dipole and it's next to another molecule that has a dipole, there is a possibility that those two dipoles will attract each other, partial positive to partial negative. If those molecules possess very strong, I shouldn't use the very strong, a very polar bond inside the molecule, then they have an opportunity to do something called hydrogen bond, which is a special type of dipole. And for you to be able to have a hydrogen bond associated dipole, you need inside the molecule to have an H bonded to an F, an H bonded to an O, or an H bonded to an N. If you have any of those three, then those, like for instance, water, we'll go back to water. Water has an H bonded to an O, and it actually has another H bonded to an O. So this attraction, well, not attraction, but this partial charge here, and these two other partial charges are very strong partial charges. So they have a strong attraction to other, in this case, maybe water molecules. So again, if it has any of those, so like for instance, here's another one. This is ammonia. So ammonia has an H bonded to an N. So this partial positive is very partial positive, and it might have a strong attraction to another, maybe water, maybe another ammonia NH3 molecule, so forth. Anyhow, it's very strong. Is it as strong as ionic dipole? Nope. Is it as strong as ionic? Nope, but it's a very strong attraction. By the way, if you have strong attractions, let's back up a little bit, make sure we didn't miss anything that we might want to think might be important here. If you have strong attractions, one species to another species, doesn't matter if it's ion, if it's a molecule, you're going to have a lot of surface tension. So that means that at the surface of the liquid, it's going to almost form a pretty not a solid layer, obviously, but if you did a belly flopper from the high dive, for instance, it would hurt a lot. Why? Because you'd have to break the surface tension of that water, all those H's hydrogen bonded to O's, one water molecule to another water molecule. Capillary action. That is the ability for a liquid to move typically upwards, like against gravity, up a very small tube. And then viscosity is liquid sticking together, thick. Think of like thick motor oil. That would have a high viscosity. Something had a low viscosity with something that would pour very easily. We also, again, our old friend Coulomb's law comes up here, and I had skipped over that, so let's go back and revisit that. Ionic dipole. So it's still the Q's, it's still the R squared. So these Q's this time could be like, that could be one of our Q's, and that could be one of our Q's. And then the R, or R squared, it would be about, water's not going to change, but the Cl minus might change compared to some other ion. And the size of that ion is going to have a part to play in how much Coulombic attraction it's going to have with the water. Okay, so here is a maybe a little better representation than mine for water with chloride ions and water with sodium ions. And be very careful on the test that you make sure that you arrange them properly. So the negative end of oxygen part of water is going to be attracted to cations, in this case sodium ions. And then the hydrogen part of water, and here's hydrogen here or here. I could keep drawing those arrows, but that's the hydrogen part of water. Those partial positives are going to be attracted to anions, in this case chloride. So I had also mentioned hydrogen bonding, that special type of dipole-dipole attraction, and they didn't really use quite a dotted line here, but I think you get the idea. It's not any of those. That's intramolecular. That is intermolecular. So the hydrogen bond is between the oxygen of one molecule and the hydrogen of another water molecule in this case. But you have to be able to have that type of bond inside the molecule to be able to give you those partial charges that are very, very strong. Okay, so again, if the molecules would have had this, or this, or in our case that, all those give you the opportunity to have a hydrogen bond capability. If you have dipole-dipole, but you don't have these three, then you're just going to have regular old dipole-dipole. So it's not really clear what these molecules are, but they're not the same atom. So maybe let's make one H and we'll make one Br. Yeah, Br is fine. The hydrogen has a plus and the Br has a minus. I'd have to go back and look at electronegativity. So maybe let's go with one a little safer than that, because I don't want to go into one that has ionic. Let's go to maybe H and S. So like H2S would have two of those types of bonds. So partial positive, partial negative, and then you would have again that, and so that partial positive and this partial negative have an equilibtic attraction to each other. Not as strong as the equilibtic attraction water to water, but still fairly strong. And then there are still items out there that we know that can become liquids or become solids. And for that to happen, there must be some ability of those molecules to attract each other. So there's a couple different ways. And this one is kind of interesting. So oxygen is a non-polar molecule. It does not have a dipole moment. So how would it be able to have any coulombic attraction with something like water, which is a polar molecule? Well, the oxygen part, and here's the oxygen part of water, has a very partial negative charge. Well, what would happen if it ran close to an oxygen molecule? Well, negatives and negatives repel. And remember that the valence shells, this sort of outskirts area of the molecule, contain electrons. And if water came really close to it, the oxygen side of water came really close to it, it would sort of repel some of those electrons, and you'd have this happen. And that is water inducing this partial positive, partial negative. Oxygen shouldn't do that, but water's making it do that. So that's called a induced dipole-dipole. Is it very strong? No, it's not. Does it last a long time? No, it doesn't. But if you've ever gone fishing, you know there's fish in the water. Fish have gills. Fish need oxygen to breathe. Where does that oxygen come from? It's in the water, dissolved in the water. How does it get there? Water induces oxygen to get to that does the water hold a lot of oxygen? No. No. Does it hold enough oxygen? A lot of bodies of water hold enough oxygen for fish to survive. And then our last category is we don't have an opportunity for ionic. We don't have an opportunity for ionic dipole, and the rest of them, all the way down to this induced dipole-dipole. But there's still molecules out there that can exist as solids. Now, does CO2 like to stay as a solid? No, it does not. But if you've seen a chunk of dry ice, you know that someone has been able to take carbon dioxide and create a situation where it can become a solid. So that means carbon dioxide has to be able to stick, have some sort of attraction to CO2. So this is the idea: London dispersal forces. And LD. People don't write London dispersal forces, they just write LDs. So everything has electrons. There's an opportunity then, if everything has electrons, so here's your nucleus, that you should have kind of a even distribution of all of your electrons, or your valence, at least your valence electrons. Well, would there be a possibility for an instant that maybe you have a little more electron density over on one particular area of the atom, of the molecule, so forth? So that would give you a possibility, and I'll just redraw that. Maybe for an instant you have a weakly partial positive and a weakly partial negative going on in that circumstance. And then maybe there's other atoms or other molecules that are doing the same thing. So there's a possibility that it's not a very strong, it's not a very permanent situation either, but there's a possibility that if the situation's right, that you might be able to notice those London dispersal forces. So if you would cool carbon dioxide down and actually pressurize it, you could get the carbon dioxide to become a solid. And that's because of London dispersal forces. And I did mention that. Very low temperatures, and we'll revisit this again, but very low temperatures, and actually you can also have very high pressures, and you can get gases that maybe what would normally become a solid or a liquid to become a solid or a liquid. Sometimes these London dispersal forces can actually be fairly strong. For that to happen, you'd have to have a tremendous amount of these situations to occur. Well, how would you have lots of those situations occur? If there was a tremendous amount of electrons. So it turns out that the higher molar mass of the compound, the more electrons it has, the more polarizability it has. Meaning the more likely it's going to have a partial negative and a partial positive somewhere. So something that's really, really, really large molar mass, like oil, might have the possibility of sticking together. And I think if you would take maybe some vegetable oil and leave it out, you wouldn't want to do that too long. But if you left that out on your table, you'd be unlikely to see a lot of evaporation. You'd likely see it stay as a liquid. Why? Because it has enough London dispersal forces to allow it to stick together and not become a gas. As opposed to if you had water, now let's not use water, let's use gasoline. Gasoline's a mixture, but if you put gasoline down somewhere, it would easily vaporize and become a gas. Therefore, it must not have as much London dispersal forces. Why? Because it must not have as many electrons that are that give it that polarizability, I guess. Here's an interesting one. We don't get to use this too often, But if the molecule, and this does happen actually with oil and margarine. Oil and margarine aren't that different, but margarine is a solid at room temperature, not a really hard solid, and it's easy to melt margarine, but it's a solid. And oil, I think you know, is a liquid. Vegetable oil is a liquid at room temperature. The differences of those is, I'll make this really super exaggerated. It's not quite this case, but they both have, for the most part, the same molar mass. So they have also the same number of electrons. So you would think they have the same polarizability. But this molecule on the right has all these locations to have the polarizability occur, where the partial positives and partial negatives, and for something else to run into it that would be able to stick to it possibly. And so this is going to be a lot more likely to be the liquid. And then this molecule here, even though it might have the very similar molar mass, very similar electrons, very similar, at least on that surface, having its same chance as London's dispersal forces, actually doesn't have as many opportunities to show this London dispersal force because its surface area is a lot smaller. So it only has those areas around there. And this would be, you know what, for this oil and margarine idea, I kind of screwed up there. This one would be most likely to be a liquid, and this one is most likely to be, I screwed up. I wrote the right thing, but I said it again wrong. Because this one has, on the right, has so much more surface area, it's going to have more London dispersal forces, solid. So this would be your margarine on the right, and the one on the left, less surface area, less chances to have those intermolecular forces. It's more likely to be a liquid, so this would be your oil over here. Okay. You can go a lot more detail into that. Someone that's in food science would maybe investigate that a little bit more. Okay, so this just gives you a little bit of a drawing about these LD forces, and then of course this would be your Coulombic attraction. And if you just had two molecules doing this, you're not going to notice anything. This would have to happen at a much greater extent for you to be able to visually observe this. And I mentioned a few of those properties that you would get because if you have lots of intermolecular forces, any type of intermolecular force. But here's a couple other ones. High boiling point. That means it's hard to boil it. These always coincide, by the way. High melting point. Vapor pressure is interesting, and that's opposite. Vapor pressure is how much pressure comes from a liquid becoming a gas. And so this is, gas here, gas pressure. So for you to have high vapor pressure, you'd have to have a material that is mostly or all gas. So this pen that I'm writing with right now, it's not vaporizing. So it's going to have no vapor pressure, as opposed to, we'll go back to gasoline. If you had gasoline in a gas can, if it's just sitting in your garage and you open up the gas can, you can probably hear a lot of gas escaping. That has high vapor pressure. We talked about viscosity already. We talked about surface tension. We didn't talk a lot about hardness and crystals with today, but we've done that before when we were talking about ionic compounds. We won't get into these biological items too much, but you've had a little bit of this in first year bio, and you'll have some of this when you go into maybe some biochemistry in college. But I think you did get the hydrophilic and hydrophobic interactions, and that was with the cell membrane. So they're definitely going to have some attractions to water or lack of attraction to water. Okay, but I just wanted to mention that there's connections to this to other sciences. You certainly don't have to know too much about this, but again, if you take more biology or you take some biochemistry, you'll learn a lot more about proteins. And think of maybe the proteins that are in an egg. So they are held together. They have a very, 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 very specific shape, and they're held together into a very specific shape. But it's a lot going on there. But at the heart of this, there are spaces that are kept together with hydrogen bonding. I'm not going to circle all these, but any of those dotted, those like pinkish dots, could represent hydrogen bonding. And hydrogen bonding can be broken. And how would you break those? If you maybe heat them up. That's one way you can break those bonds. And when you break those bonds, it's going to give it a whole new shape. And that shape won't have the same function. It has to be in this very specific structure for it to have the function that it's supposed to have. And so if you break that shape, you denature the protein, and then it no longer functions the way it's supposed to. And you would notice that with an egg, and maybe not with the functioning part, but you would definitely notice that you denatured it. If you cooked an egg, it definitely looks much different than you had with that raw egg. But anyhow, that is with hydrogen bonding. Okay, so these are kind of questions you would get, maybe multiple choice. I don't think these are really free response questions the way they're set up here. So which of the following can form hydrogen bonds with water? So you have to have an H to an O, an H to an F, or an H to an N that's in the compound. So that's out, that's out, that's out. This looks like, this first one here looks like it has a possibility, and this one here looks like it has a possibility. But of those two, the only one that truly is going to work is this one, and I'll show you both. So here is the first molecule, and this is why we visited a little bit of organic chemistry. So nowhere in that molecule is there an O bonded to an H. So there's no opportunity for hydrogen bonding to occur. But the second one I had, that's a carboxylic acid there. And there we go. So this part of the molecule has a very partial negative and a very partial positive. So no, it's not the entire molecule. But that area has a very, very partial negative, very, very partial positive, and therefore would have a strong Coulombic attraction to water. Which of the following is most likely to exist as a liquid at room temperature? So I should have probably given you a little more information. Which of the following is most likely to exist as a liquid as opposed to a gas? And so if you want it to be a liquid as opposed to a gas, you need to have something that has high intermolecular force. So this molecule here is non-polar, so it only has a chance to have London dispersal forces. Usually London dispersal forces by themselves are not enough for it to be a liquid. C's and H's. Anytime you have C's and H's, no matter how they're set up, in this case it looks like this, that's going to be symmetrical. Yeah, I didn't write the H's in there, but they're in there. That's going to be symmetrical. If it's symmetrical, that's London dispersal forces. So those two are out. So that gives us now methyl chloride. So I'll just kind of amend this a little bit. Okay, so now this is not symmetrical. this is this has an asymmetry to it, and we could say that there's a partial positive and partial negative right there. And that might give it an opportunity to become a liquid more than the other two. Rank the following compounds from lowest to highest boiling points. So the lowest boiling point is going to have the lowest intermolecular force. The highest boiling point is going to have the highest intermolecular force. So we could start either direction. Let's start probably the easiest. Barium chloride is ionic, so it's going to have a tremendous boiling point. I don't know what it is, but you're not going to be able to melt it with your oven. That's with the temperature of your oven. So we'll go like that. So barium chloride has the highest boiling point. Maybe we'll keep going in that direction. So is there something else that has more than just London dispersal forces? By the way, if you have electrons, you have London dispersal forces. So it's a good time to mention that everything has London dispersal forces. So if someone asks you, hey, what are all the intermolecular forces that this possesses, you'll say London dispersal forces, and then keep on going. Okay. By the way, people typically only use that, even though I guess I just said everything has London dispersal forces. If it is, if it's covalent, if it's any type of covalent compound, people will attach the London dispersal forces. When it gets into that lattice structure, no one ever mentions the London dispersal forces in those cases. HF has that special type of dipole called hydrogen bonding. Why? Because it has an H to an F. Remember, if it had an H to an F, H to an N, or H to an O, it can have hydrogen bonding capabilities. So now we're down to 3 items left, and this one is asymmetry, has asymmetry. So it has dipole. And then we're down to neon and hydrogen gas. So those are both symmetrical items. So now it's about London dispersal forces. And what gives you more or less London dispersal forces? The number of electrons. So neon has more electrons, and hydrogen has the least amount of electrons of anything. So there's your categories. Your rankings. Okay, now this time we have a hydrocarbon. We have a hydrocarbon now that has a alcohol group, and we have another hydrocarbon with a alcohol group. We'll start with this one over here. Hydrocarbons by themselves are going to be symmetrical, and so London dispersal only. These two have hydrogen bonding capabilities with the OH, but this one here has more electrons than this one does. So methanol would be next, and ethanol, would be next. So here's another typical question. AP, we love our exceptions. So it looks like things should go this way. Let me move that up just a little bit. So the boiling points should get lower and lower and lower and lower as you have, we'll just look at these two. This one has the least electrons. This one has the most electrons. So what does that deal with? That deals with LD forces. So if you have the least number of electrons, it's the least polarizable of the 4 in this list, so the lowest boiling point. SNH4, most electrons, most polarizable, most LD forces. Well, that's great, but then these other things don't go like that. Looks like we have these aberrations here, these exceptions. What the heck is going on here? How come they're not continuing down the line with that LD idea? Well, because this one has an HO, this one has an HF, and this one has an, to keep it the way I had it before, we'll go HN. HO, HF, HN. What kind of things going on there? Remember, that means it has hydrogen bonding capabilities. Hydrogen bonding capabilities are very strong. So these three are going in that direction because the number of electrons keep changing and the amount of LD forces keep changing. They all have dipole because they are bent molecules, but the LD forces change as the number of electrons change. And then we get to the exception part, and the reason that exception part occurs is because these also have special dipole called hydrogen bonding. So I think we probably answered some of these questions already. And you can go through and try to answer those again, but I think I had just answered those and maybe more concise than just 3 separate questions there. And it looks like that's it. So you definitely need to practice with your molecule building. You're recognizing if it's symmetrical or asymmetrical, and then understanding if it has different types of intermolecular forces.